Thank you very much, and it is a pleasure for me to introduce tonight's speaker, Professor Oded Aharonson. He is a professor in planetary sciences here in the Division of Geological and Planetary Sciences at Caltech. He received his Bachelor of Science and Master's at Cornell University in Applied Physics. He received his PhD in Planetary Sciences at the Massachusetts Institute of Technology. And after that, he did a year stint in the Israeli army before coming back to America. And since arriving at Caltech, he's worked on a number of planetary problems relating to geomorphology. So he's investigated lacustrine and fluvial environments on the surface of Mars, as well as investigating the stratigraphic record to indicate past climate changes on Mars. And he has also participated in several spacecraft missions, including the Mars Exploration Rover, the Lunar Reconnaissance Orbiter, and recently the Cassini mission to Saturn. And tonight's talk is going to focus on one of the most exciting moons in our solar system, Titan, and his talk is going to be on Titan's lakes and climate cycles and other worlds. So please help me give a warm welcome to Professor Oded Aharonson.
This is really fun for me, especially fun for me to see all these kids in the audience. And actually, I want to get started by figuring out who's the youngest kid in the audience. How old are you? 7. How old are you? 11. What do we have back there? 8. Do we have anyone that beats that? How old are you over there? 7. All right, so we got a tie for 7. Anybody could beat 7? All right, well, welcome. It's really nice to see you guys here. I really appreciate you guys coming, especially the kids. Can we get the lights, or am I supposed to do that? Okay, great. So I want to tell you a story today. I want to tell you a story about Titan, this amazing moon of Saturn, as Jennifer said. And also, as Jennifer mentioned, I actually got my start working on Mars because when I was going to graduate school, Mars was the new Earth. We had an armada of spacecraft going to Mars, and it was really exciting to look at all the data that was coming back down from Mars. Mars is very similar to the Earth in some respects. But many of you in the room who are participating in the Titan study that is going on campus know that Titan is new Mars. So I'm actually going to talk about Titan, not Mars, and I'm actually doing the transition these days myself, although most of today I spent actually discussing the results from the Mars exploration rovers. Okay, so this moon of Saturn, Titan, over the last few years we've actually learned a lot of information about Titan that we didn't know before. Before I go further, I want to acknowledge that some of the information that I'm going to tell you is from my co-authors. There's actually a prestigious list of co-authors there, members of the National Academy, the guy who runs JPL. He's also the PI on this instrument, Charles Alachi, and Ralph Lorenz, Mike Allison. But I particularly want to acknowledge the contribution of my student Alex Hayes, whose work contributes to a lot of what I'm about to show you. Okay, so the map that I showed you on the title slide there was a synthetic aperture radar map of Titan. But actually, until very recently, we didn't know very much about Titan. Titan looked like this. This is a Hubble Space Telescope image of Titan. So this is what Titan looks like from the Earth. And actually, most of what you see here is, of course, Saturn. And this is, I think, a beautiful photograph of Titan casting its shadow on Saturn. And you see that even from the Hubble Space Telescope, which is an extremely precise and high-resolution instrument, Titan basically looks like a bland dot in the sky. And for many years, this is pretty much all we knew about Titan. We could try to figure out where the color of Titan comes from. Titan was discovered in 1655. It was discovered by Huygens, who I think was basically jealous of Galileo. Galileo had discovered his satellites several decades earlier, and Huygens decided he wanted to do something like that too. So he built a telescope with some help, and then he found Titan. So that was his Galilean, the equivalent of his Galilean satellite. And some years later, actually not until the turn of the 20th century, it was realized that Titan had an atmosphere. basically by seeing that the limb of Titan is darkened, as you see in this image. And we also realized that there's some stuff going on in the atmosphere. There's some cloud. There's a polar hood of clouds that you can see in this picture too. But we really couldn't unveil Titan until recently and look at the surface and what's going on under this atmosphere. So people did experiments. I have to show this picture on the right because people were doing experiments in the lab trying to figure out what gives Titan this strange color and what it's made out of. So they took the things that we thought were in Titan's atmosphere, basically hydrocarbons and nitriles and compounds like that, put them in test tubes and tried to subject them to Titan temperature and radiation and pressure environments and basically cook this stuff up and see what comes out. And indeed, these hydrocarbons started joining up and making ever longer chains of hydrocarbons and ever bigger particles that form the orange hazes that give Titan its color. When I was at Cornell, this stuff was going on at the basement, which is why I have to show this picture. And Carl Sagan was, of course, very interested in understanding Titan, and he even conjectured about life forms living in this soupy, tarry material that's floating around on Titan. And he's the one that actually, I think, coined the term tholin after the Greek muddy, because this stuff is like mud. It's like tar that these particles just grow and become sticky and eventually fall out of the atmosphere. So this is more or less what we could tell, right? We could look at Titan through a telescope. We could do some experiments in the lab, but we really didn't know very much about this world until much more recently. And I'm going to argue that now that we know a lot more about Titan, it really fits squarely within the picture that we have of the terrestrial planets, places like Venus, or Earth or Mars, places where we see active geology, active cycles, active geologic cycles, active hydrologic cycles, places with thick atmospheres in the cases of Venus and to some extent the Earth and to a lesser extent Mars, but really places that have all of these processes that are very familiar to our own. I think Titan really fits much better among these planets, these objects in the solar system. So everything changed when Cassini launched, and I don't know if you can see this. There's a date on the corner of this picture. In October of 1997, this was a spectacular night launch that sent this flagship mission. I'll show you a picture in a minute of what Cassini looks like. This pretty large spacecraft in normal terms to Titan. So this was launched from the Cape. And here's what the spacecraft looked like. It actually had two parts. This is an artist's conception, of course, of the spacecraft. You see it has a high-gain antenna that's used to communicate with the Earth. And it has two parts. One is the main spacecraft, and then before actually doing many of its measurements, after doing some of them, but before doing much of its mission, Cassini separated the Huygens probe, named, of course, after Huygens. And this probe actually separated from the spacecraft, descended through Titan's atmosphere, and made measurements. So the Europeans built the Huygens probe, JPL, just up the hill, built this thing, and both performed incredibly well, as you will see in the coming hour or so. So Huygens probe separated from the spacecraft and started its descent. During the Cassini mission, this satellite, that's Titan over here, that was originally actually thought to be bigger than Ganymede. These are the Galilean satellites over here. These are the four major satellites of Jupiter. And here is our own moon, and I think that's Triton over there in the corner. These are sort of the magnificent 7 satellites in the solar system. I think you can add other ones now if you want. Enceladus has, of course, got fascinating jets coming out of it. So there's many, many interesting objects in the solar system. These are sort of the 7 big ones. And you can see that we've seen the surfaces of many of them. There's Io, the pizza satellite, that has volcanoes on it, and Europa that probably has a liquid water ocean. Titan looked pretty boring, and then when Cassini got there, it sort of unveiled the atmosphere, and we were able to look underneath these thick hazes and clouds. What's depicted here is a stellar occultation. This is a star passing behind Titan. Really, more appropriately, I should say this is Titan passing in front of a star. Or really what I should say is this is the Earth moving, and therefore the projection of the star behind Titan changing, because that's the thing that moves the fastest out of all 3 of these things. So as the star passes behind Titan, we can measure the light curve. We can see how the light gets attenuated as it passes behind the atmosphere and then eventually the solid body of Titan, and then comes out the other side. So initially, with the atmosphere, we actually thought that Titan was the largest moon in the solar system. It was bigger than Ganymede. But then when we realized exactly where the surface was, when we penetrated beneath the atmosphere, then we realized that Titan's actually slightly smaller than Ganymede. So it was demoted a bit. But nonetheless, I think there's a lot to be learned from measurements like this, from the stellar occultation. One of the nice things about a stellar occultation actually is when the star is directly behind the object, then the object's atmosphere can act like a lens, and the light actually travels all the way around the object and refocuses on the other side, and then you get this bright peak on the other side, which the spectrum of which is actually very indicative of the composition of the atmosphere, because most of that light, all of that light passes through Titan's atmosphere. So there were some investigations like that as well. And then of course, Cassini unveiled the surface. And I just want to take you through some of the amazing discoveries on this strange place. Now, if some of you read the description of this talk, you realize that Titan is significantly further from the sun than we are, and therefore is much colder. The mean surface temperature on Titan is 92 Kelvin or so, 92, 94 Kelvin, compared to something like 300 on the Earth, right? So it's like minus a couple of hundred degrees Celsius. So it's a place where water ice, which is what most of the exteriors of the satellites is made of, is as hard as rock, because at cold temperatures, ice is very, very hard. So the rock on Earth is the equivalent ice on Titan. And so the temperatures are completely different. The normal materials that we're used to here, ice is very, very hard, and things like methane or other hydrocarbons that on the Earth are found in the form of gas, on Titan it's so cold that they can be found in solid or liquid form. So this world that has exotic chemistry and exotic thermophysical conditions turned out to be all too familiar, as you'll see. But one of the first things that Cassini showed us is this incredible diversity of surface features, surface spectral types, surface geologic types that began to be more and more familiar as we looked at them closer and closer from our own terrestrial experience and my Mars experience, actually. So I think it's really interesting to me. It's amazing to me that even though the physics and the thermophysics and the chemistry are so different, ultimately the laws of physics lead us to have this geology on Titan that's all too familiar. And as you'll see, many of the processes that are all too familiar to Earthlings. So this is a map from VIMS, the imaging spectrometer, that shows that there are many units of different colors on Titan, different brightnesses, and as you'll see close up, different geologic origin. Another thing that Cassini brought to light is the fact that it is likely now that Titan has a liquid water ocean underneath an icy crust. There are several measurements that one can imagine to resolve this problem of whether there's a liquid water ocean. One way to do it is the way you tell whether an egg is hard-boiled or soft-boiled. Does anybody know how to do that? You spin it, yeah. So the way something spins depends on whether it's squishy on the inside or not. If the egg is totally hard-boiled, it spins as a solid object. If the egg is soft-boiled, then the interior of the egg wobbles around sometimes a little bit differently than the exterior. So you can try to stop it, and the interior keeps going, and the egg starts spinning again. The same thing can be done with Titan by looking at great detail at its spin state and figuring out whether it wobbles around in ways that indicate that it's squishy on the inside, and there's people trying to do that. There are also electrical measurements that try to determine whether there are fields that are associated with the liquids inside Titan. So I would say the jury is still out on this one, but it seems likely that Titan may have a liquid water ocean trapped between the silicate interior that's at least partially differentiated, partially separated out from the ice, and the icy exterior that we now see. So Cassini has a synthetic aperture radar instrument on board. I already mentioned that, and this instrument is going to be to play a major role in the rest of this talk. Synthetic aperture radar means that there's a an antenna that looks off to the side of the spacecraft and bounces radar energy at a high angle, so it's looking to the side, at a high angle off the surface. You can imagine that most of that energy goes off into space because it bounces off, but some of that energy, if the surface is rough, bounces back at the radar. So I want you to get used to looking at these radar images like the one that you see here. Places that you see bright radar returns, it must mean that the surface is rough because some of the energy came back to the instrument. Or it must mean that they have electrical properties that promote the return of radar energy, electromagnetic energy back to the instrument. So bright areas either have a high dielectric constant or rough in technical language, and dark areas have a low dielectric constant or very smooth. So what you see here is a radar image of some of the equatorial portions of Titan. And actually, much of the equator of Titan looks like this. It's quite incredible. These are dunes, okay? And they should be very familiar to you if you fly over the desert or even walk in the desert. You'll see longitudinal dunes, and the characteristic size, they're about 1 kilometer or 2 apart, about 1 mile apart, and their heights, about 150 meters, say 500 feet or so, are entirely recognizable from our terrestrial experience. Okay, so if you were to fly a radar over the Mojave Desert, you might see dunes just like this one that you see here. So they're called longitudinal because these dunes are all parallel and elongated in direction parallel to the wind, and you see that the wind deflects them around topographic perturbations, like mountains that you see over here. So these dunes were some of the first observations that Cassini made, and again, they look just like terrestrial dune fields. Here's an example actually taken from the shuttle. This is an astronaut taking a picture out of the window of the shuttle, and indeed, you can see dune fields, in this case in the Namib Desert, that have similar wavelengths, similar spacings to the dunes that we see on Titan, and similar heights, and so forth. The material that makes up the dunes on Titan is probably some combination of frozen ices. On Earth, of course, it's sand. So again, at these very different temperatures, it's remarkable to see how the materials actually end up behaving in a way that leads to all too familiar geologic forms. I think one of the most important things to realize about Titan, sort of just sitting at your desk and thinking about what's going on there, is summarized in this plot. I'm going to take you through this, and I really hope that you understand that you're going to understand by the end of this talk the plots that I'm going to show. I don't want to confuse you. So this is height. This is the pressure in the atmosphere, which is equivalent to height. Here I'm even writing down how high I am in the atmosphere of Titan, 50 kilometers, 150 kilometers in the atmosphere of Titan. And here is the equivalent height on the Earth. Okay, so this is 10 kilometers on the Earth and 25 kilometers on the Earth. And on the x-axis here, we have temperature. So it gets warmer over here, and it's colder over here. So the boiling point, or the freezing point of water is 273 Kelvin. That's right over here. The boiling point of water is 373 Kelvin, 100 C. That's over here. So there's something very important about the atmospheric profile of the Earth, and that is that the temperature-pressure profile, how pressure changes with, how temperature and pressure change with height on the Earth, makes the atmosphere of the Earth pass through the phase diagram of water. Right? You know that the boiling and freezing point of water cross this curve. And this is the troposphere of the Earth, where the temperature gets lower, and the stratosphere, and so forth. So there's opportunity for water on the Earth to evaporate and to recondense in the atmosphere and rain out. Okay? This fact that our atmosphere passes through the phase transitions of water from ice to liquid to vapor is probably one of the most important facts that allow us to inhabit this planet. It means that we can have a water cycle that evaporates water in parts of Earth and in some seasons, recondenses it, and delivers it back to the surface. So we can mix up the stuff on the Earth by mixing up the water. The same thing is true about Titan, except not with water, with methane. So this is the pressure and temperature profile of the atmosphere of Titan, and it too crosses the phase diagram, but of methane. So the same opportunity exists on Titan for methane to evaporate off of its lake, recondense in the atmosphere, rain out, drain on the surface, and as you'll see, form lakes. So just sitting at your desk, and people actually did this, you can conjecture that Titan might have all of the same hydrologic processes that the Earth might have, except the working liquid on Titan wouldn't be water, it would be hydrocarbons, and in particular methane. And indeed, that's exactly what happens on Titan. So Cassini took some pictures of the surface, and here is one of the ones in sort of the mid-latitudes of Titan, and you can see channels. So as promised, the water must drain out from the atmosphere, pool on the surface, and drain through these channels to the low-lying areas. And again, just by way of comparison, to see how familiar the dendritic nature of these channels that we find on Titan are, here is a picture that a friend and a colleague of mine, Ralph Lorenz, took from an airplane on the way from Tucson to LA, and you recognize these channels. I'm guessing, yeah, I don't exactly know where this is, but you recognize the dendritic forms, the merging channels. All of these morphologies look familiar between Titan and the Earth. So I'm going to tell you a little bit about what happened with Huygens. Here's Cassini here, and then Huygens is going to separate out from Cassini with it's going to give it a little bit of a spin so that it stays stable. And then a lot's going to happen pretty quick over here. Huygens is going to enter Titan's atmosphere. It's going to go in supersonic speeds. Titan's atmosphere is actually very friendly to landing because it's very large and dense, so it's like a soft cushion to land in. You see it's penetrating through the Titan's atmosphere and heating up because it's traveling at supersonic speed, so it's better to have a heat shield to protect it from these 1,000 degrees or so that the heat shield gets to. Then the first parachute opens just to slow it down below supersonic speeds, and the heat shield separates. Then there's a second parachute that opens in order to slow the spacecraft down relative to this back shell that needs to separate from it. So this has to travel slower than this in order for the two to come apart. This parachute is still not quite big enough to slow the spacecraft down to where it needs to be upon landing. So there's going to be another parachute, and there's the third parachute that opens. All of these things have to happen exactly at sequence. You can see the spacecraft was acquiring the surface using radio waves. That's how it knew how high it was in order to deploy this last parachute. And then eventually Huygens comes to rest at actually a pretty comfortable speed, just a couple of meters per second, as if I was just to drop something from this desk. So Huygens landed on the surface, and nobody knew what to expect. Okay, nobody knew what it was going to see. And in fact, at Caltech, Rocky killed us. This is what we were doing. This is the whiteboard at the kitchen across the street in the Geological and Planetary Sciences building. And as you can see, we were taking bets on what Huygens was going to find on the surface. So there were several graduate students that thought he would just land in some ice. Some people thought he would land in this tar, in this strange muddy material that Carl Sagan worked on. One guy thought he would actually splash down in some liquid. Some people thought we wouldn't know what it landed in and maybe never know what we landed in. My own student, I guess, shares my skepticism, and he thought he would be dead on arrival. And a very famous Caltech professor thought he would be eaten. So you see, this is sort of a funny chart, right? But I put it in this talk because I think it actually means something. And what it means is that we had no idea. I mean, smart people had no idea what we were going to find. The range of possibilities was just extreme of what we were going to find on the surface of Titan. Here's what we did find. This is the image that Huygens took upon landing. This is the image he took on the way down. So let's just talk a little bit about this. This is really cool. Huygens actually ended up spinning more than he was supposed to on the way down, and he was even spinning the wrong way on the way down, which was a little bit annoying to try to paste together all the images that were acquired. But eventually people put together this puzzle by actually printing out all the pictures and arranging them on the desk. And this is part of what they saw. I'll show you a little bit of bigger view in a minute. But you see that on the way down, we saw this extremely detailed. Actually, we've never seen a more detailed drainage system on Titan since then. You see that there's many branches to this drainage network that empties from the highlands over here down to the valley below. And then Huygens landed somewhere over here relative to this image, down in the bottom of this drainage valley. And this is what it saw. So what do we see here? We see some sort of bouldery-looking things that are maybe somewhat rounded. My guess is that, and this isn't proven because we haven't sampled any of these things, but my guess is that these are rounded boulders of water ice that have been transported down into this valley by the fluvial system over here. So, and they were able to round because they were tumbling on the way down. This happens on the Earth all the time. That's why we see rounded stones near the mouths of outwash valleys. And then there is this sort of sandy material that might be atmospheric particles that fall from the atmosphere and cover the surface. So this actually, to me, looks like a pretty typical outwash plain on the Earth. And again, I think for a geologist to look at this picture, it's both exhilarating and strangely familiar at the same time. You know, we travel all this way to this extremely crazy, cold, crazy chemistry place, and we find things that look all too familiar geologically. This is the full set of the descent images. So you see the channel network that I mentioned over here, and then you can see there's other mountains and sort of a valley in between them over here. It's a little bit hard to see exactly what's going on here, but you can imagine that scientists peer over this and try to interpret the relationships between these various units. So we discussed that the atmosphere of Titan goes through the phase transition of methane, and that therefore there's opportunity to evaporate and recondense methane. So the picture that I want you to have in your mind is sort of cartooned on the screen here. So there's methane that might be coming out of the surface. There could even be methane coming out of cryovolcanoes, volcanoes in ice that emit things that are volatile in Titan's atmosphere, that tend to evaporate in Titan's atmosphere. So there's a source of methane from the ground up into the atmosphere. That vapor then can condense and form clouds, or you can travel even higher in the atmosphere and form fogs and hazes that are actual particles of ever more complex hydrocarbons as they stick together. And then you can have occasional impacts coming in and disturbing things, and rainfall can pool and form channels and lakes on the surface. So this is sort of like a cartoon of all of the processes that are happening on Titan, and you notice that all of these also happen on the Earth. I'm going to focus for the rest of the talk about the lakes. I think the lakes are really cool. There are several kinds of lakes on Titan that we were able to identify, and this is work by my student Alex Hayes. And Alex managed to map all of the lakes that we sampled over the northern hemisphere. What I mean by sampled is we covered with SAR images, with this radar instrument. So this is what the typical lakes looks like. This is what most of the lakes look like. They're radar dark. Okay? Why are they radar dark? So they're dark because the surface of the lake is smooth. And the radar energy, remember we discussed this before, when it interacts with a smooth surface, most of the energy bounces off and never returns to the spacecraft. These lakes are so dark that, in fact, they're right at the noise floor of the instrument. We get no energy back, as far as we can tell, from most of these lakes. So they're totally radar dark. Okay, and they have these sort of lobate shapes and some size-frequency distribution that we measured. These are the little ones over here. Then there's some enormous ones that are seas that are over here, Kraken and Legia Mare over here. We even gave them names. There's another kind of lake on Titan, and they look like this. They have similar size-frequency distribution to these little lakes. They have similar shapes. They occur at the same latitudes. You see they're plotted in green in this plot over here, in this map of the northern hemisphere of Titan. So they share many of the properties as the dark lakes, except one. They aren't dark. Okay? They're actually radar bright. You see they're brighter than their surroundings. So the interpretation for those lakes is that they were formerly filled with methane. I feel like there's a Prince joke here somewhere. Lakes formerly filled with methane, and now they're empty. Okay? And the same instrument that can measure the returns from these lakes can also operate in an altimeter mode. So instead of just flying over the lakes and bouncing the radar off to the side, we could look straight down and measure the time of flight of the energy from the spacecraft to the ground and back to the spacecraft. Just measure how long it takes. So here is the altimetric profile, or the height of the topography across this lake. And you see it's a big hole in the ground. Okay? This is so this hole in the ground, we can measure its depth, and it's 200 or 300 meters. So this is just like these lakes, except there's no methane in it, and it's 200 or 300 meters deep. Okay, I want you to remember that. This fact is going to come back later. But the important thing to remember, just to reiterate, is that this is the typical height or the typical depth of lakes on Titan. So how do we know it's liquid? There has actually been, I think, a spectacular image taken by the spacecraft very recently. We all thought it was liquid, but I think there are a couple of measurements that were made that sort of sealed the case. This is one of these spectacular images that were taken, and anybody who's flown over the ocean recognizes the specular glint that this is the sunlight that's reflecting off one of Titan's polar lakes over here and hitting the spacecraft. Okay, so this is the specular point on Titan. If you fly over the ocean, you can see the same thing happening on the Earth. You can see the sunlight at a particular spot, really, really bright. So this is the specular glint of one of these lakes, and that was one of the ways in which we can conclude that it's liquid, because you only get a specular reflection if the surface is extremely smooth. The other way we know that it's methane, this is a little bit complicated, but I'll just tell you about this spectrum. So we look in detail about the light that's reflected back from these lakes, and we can only look where methane allows us to look, because most of the atmosphere has methane in it. So we can only look in the places in the spectrum, in the spectrum of light that penetrates through the atmosphere, where methane doesn't absorb all the light. So there are some windows, they're called, in the spectrum that allow us to peer in the surface. So obviously we're not going to find methane on the surface very easily like this, because if we see if there is any methane there, it would have all the light that would have interacted with the atmosphere and been absorbed. So what we know for sure is that there is ethane there, a higher hydrocarbon. So this was a very famous paper that was published that showed that there were very distinctive signatures in the spectrum of light that was returned from these lakes that were consistent with there being ethane in the lakes. Okay, so we know for sure there's some ethane there. We all suspect that there's also methane there, but we can't measure the methane directly on the surface. We can just do calculations that tell us that it should be there. One thing we noticed at Caltech is that many people noticed this, but we thought of an explanation, that all the lakes that we started to see as we were mapping Titan were in the northern hemisphere. So what was happening was the spacecraft was flying by Titan every so often. Every few weeks or every couple of months, we would get another pass over Titan. And a pass is one of these strips of radar image that you see here. And so you can imagine the sort of excruciating process of learning about Titan one of these strips at a time. Okay? You don't get the whole picture at once. It just reveals itself over year periods. And in the beginning, we were flying over the northern hemisphere more often than the south. So in the south, we had basically one pass, and we saw there was actually one lake in the south. We saw there was the very first lake that we saw was this one. It's called Lake Ontario, Ontario Lacus. And then we started getting a lot more data about from the north. And the more data we got from the north, the more lakes we saw in the north. Okay? And we started noticing that there are a lot more lakes there than in the south. But we didn't have very much data in the south. And then over time, over the next year or so, we kept building up more and more data in the south. So our initial guesses that the north had more lakes, in the beginning we weren't sure if this was right or not. But then as we got more and more data, we gained more and more confidence that indeed there was this mystery. Why are all the lakes in the north of Titan, and there are very few lakes in the south? And I'd like to talk about that now. So first, I'll tell you that this isn't a statistical artifact. Okay, we've looked at maybe half the surface on Titan. This is a graph that shows what fraction of the area of Titan has lakes on it, and what fraction we've looked at. But we've looked at about half the surface of Titan on both sides of the planet, and on the north we have maybe a factor of 20 or more lakes than in the south. Maybe as much as a factor of 100 more lakes in area in the north than in the south. And it's not luck. This is statistically robust result. So the next thing we thought of is maybe the two hemispheres of the planet have different elevations. So why is all the water in particular places on the Earth? Because the ocean floor is lower than the continents, and all the water drains down to the lowest places on the Earth. So we thought maybe Titan has a dichotomy in the topography. Maybe one side of Titan has different topographic properties. Mars is like this, by the way. Mars has one side that's low and one side that's high. Maybe Titan is the same way, and all the liquid on Titan, methane, drains to the north. Turns out that's not true. We actually, the same instrument, again, this radar instrument, was able to map the global topography of Titan using this altimeter mode that I mentioned before. And it showed that there's no big differences in the north and the south. They don't look exactly the same, but there's not a big hole in the north that doesn't exist in the south. Actually, both of them have relatively lower topography relative to the equator. And there's also no big difference in the drainage properties of the north and the south, as far as we can tell. They both have mountains. They both have opportunity for water to drain down and pool in basins. It's possible that there's something about the subsurface that we haven't seen yet that prevents methane from permeating into the ground, from infiltrating into the ground on one side of the planet and on the other side. But we haven't seen it. We have no evidence for it. It's just conjecture. And as far as I can tell, I think it's just sort of hiding our ignorance somewhere else. Instead of saying that there's an unexplained dichotomy in the lakes, we're saying there's an unexplained dichotomy in some mysterious impermeable boundary that prevents the liquid from draining. And that's not very satisfying. So I can't rule it out, but I don't think that's a very satisfying explanation. So it's not the topography. One idea that was actually suggested was that this is a seasonal effect. So I need to explain this. So the Earth has seasons because its spin axis is oblique to its orbit. So sometimes the northern hemisphere faces towards the sun, and sometimes the southern hemisphere faces towards the sun. So if this is the sun and this is the Earth goes around the sun like this. And if this is the northern hemisphere, it's northern summer when the Earth is on this side, and it's southern summer when the Earth is on that side. Same thing is true about Titan. Not exactly the same, because on Titan, it's all due to Saturn's orbit. Saturn is oblique, with a similar obliquity, actually, to Earth's obliquity. So it, too, has seasons. And Titan is in Saturn's equatorial plane. So if this is Saturn, and this is Saturn's equator, Titan is sitting there orbiting Saturn almost exactly in Saturn's equatorial plane. So it, too, is tilted towards the sun sometimes and away from the sun other times, okay? It's basically along for the ride. Whatever Saturn does, Titan does. And as Saturn goes around the sun, so does Titan, because Titan orbits Saturn. And Saturn does so every 30 years. So the Earth goes around the sun every 1 year. Saturn goes around the sun every 30 Earth years. So it's slower, but there's still seasons. And they're actually comparable magnitude to the seasons on the Earth because the obliquities are similar. So one idea is maybe all of the methane in one hemisphere evaporates, say in summer, for example, travels through the atmosphere to the other pole, recondenses, rains out, and every season all the methane goes from pole to pole. This was actually suggested by Jonathan Lenin as the reason for why all the methane may be found, and all the clouds too, we see an asymmetry in the clouds sometimes, all may be found in one hemisphere rather than the other. So people try to do very precise models of this process. So you can imagine, what do you need to do that? You need to figure out the energy budget in the atmosphere. Now, I'm not going to take you through this cartoon. I just want to indicate to you that there's all sorts of energy fluxes. There's an energy that comes in from the sun, that comes into the atmosphere. Some of it gets absorbed in the atmosphere. There's re-emission in the atmosphere. Some of it may interact with the surface. Eventually, some of that energy leads to the evaporation of methane on the ground. Okay? So people try to calculate exactly what fraction of the solar flux, the solar sunlight, reaches the surface and evaporates methane. And they get an answer. The predictions from global circulation models, these are models similar to the models that are used to understand how the Earth's climate behaves, is that this is how much energy, a couple of watts per square centimeter, is available to evaporate methane at the surface of Titan. Does anybody know how much energy the Earth gets from the sun, roughly? Yeah, 1,000. I heard it in the back there. It's about 1,000 watts per square meter, okay? So this is a tiny fraction, because Titan is so much further away. This is a tiny fraction of the energy that the top of the atmosphere gets. And not even all of that energy makes it to the surface on Titan. Not all of that energy makes it to the surface on the Earth. More of it does. But this is a tiny fraction of that. So I can ask how much energy it takes to take one molecule out of the liquid phase and put it in the air. Okay? That's called the latent heat of fusion, or the latent heat of evaporation in this case. And if I take that number and I divide the amount of energy that I have available by that number, then I can figure out how much methane I'm going to lose in one season. And the answer that all of this long story ends up with is several tens of centimeters per year, maybe up to a meter of methane per Earth year can evaporate from these calculations, okay? So about a meter per year, or maybe over the Saturn season, which is half of 30 years long, maybe 15 meters, maybe I made some factor of 2 mistakes, so maybe 30 meters, but probably not much more than that. Okay, so now you understand why I told you to remember how deep the empty lakes were, right? If I can only move around something like 10 or 20 or 30 meters of methane every season, maybe I could move some of the methane from pole to pole every season, but it's not likely, I think, that you could move 200-300 meters of methane, and these are just the little lakes that are 200 or 300 meters. The big seas are probably much deeper than that. So I think it's not likely that this is the right explanation. First of all, because yes, you do move some methane back and forth, but it's not enough. There's another small problem with it, and that is, okay, suppose I turn all my knobs and I make the methane, even more of the methane move from pole to pole. How do I move the hole in the ground from pole to pole over every 15 years? Okay, it's one thing to move the liquid, but how do you move the geologic feature from pole to pole? So the last reason that I'm going to tell you is the reason that I think is right. I gave you a few reasons that I think are not the right explanation. This one is crazy, but I think it's the right one. I didn't tell you a fact that you need to know, and I'll try to explain this one about Titan. In addition to Saturn's orbit being oblique to the Sun, so in addition to the spin axis having an angle with respect to the orbit, it's also eccentric by a lot. Something like 6%. It comes closer and further from the Sun every year by 6%, or actually twice that at the extremes. Okay? And there's an alignment such that every time it's close to the Sun, the southern hemisphere faces the Sun, and every time it's far from the Sun, the northern hemisphere faces the Sun. Okay? It's actually very similar to Mars, except the eccentricity in this case is even higher. So you can imagine then that southern summers, whenever the south is facing the Sun, are hotter than northern summers, right? Because it's closer. They're also shorter because the orbit speeds up when it comes close to the Sun. And northern summers are more subdued. And the same thing is, or with the opposite thing is true about the winters, okay? So southern summers are short and intense, and northern summers are long and subdued. Does this make sense to everybody? This is the most important fact. I want to make sure this is clear. So as this is Titan or Saturn over here, it doesn't matter. This is the Sun. As it comes through perihelion, one side of the planet, perihelion is the closest point to the Sun, one side of the planet, namely the southern hemisphere, faces the Sun, and it's southern summer, and it's intense. Here I'm writing down the seasons in the north, so I'm actually calling it winter, but it's summer in the south. And then on the opposite side of the Sun, it is summer solstice in the north, so it's winter in the south. And the seasons are asymmetric. Okay? So you can imagine that there's opportunity for the summers in each side of the planet to be different. The same thing is actually a little bit true in the case of the Earth. It's more true in the case of Mars, and it's really true in the case of Titan. Titan doesn't get that much energy. We said it only gets like 7.5 watts per square meter of energy from the Sun, of which only a couple of watts per square meter make it to the surface. But this is a plot of time, so this is one Saturn year going, okay, so this is, and this is latitude. So this is the South Pole, and this is the North Pole. And you see here is southern summer, where all the sunlight comes. This is the season of southern summer. And this is southern winter, when there is no sunlight. This is permanent polar night in the south. Okay, does everybody understand how to read this plot? I'm going to show you several of these plots, and I want to make sure they're clear. So this is time, and this is latitude, and this is 1 year, and this is pole to pole. Okay? So you see that southern summers are intense. They have more energy than northern summers, more power than northern summers. The south gets something like 7.5 watts per square meter at peak, and the north gets only 6 watts per square meter. Okay? It's a difference of about 25%. Remember I told you the eccentricity is like 5 or 6%. So the difference is 12%, and it's actually peak to peak, a difference of like 24 or 25% in the amount of sunlight that's available to evaporate methane in the south versus the north. What really matters is actually not much how you evaporate, but how much you evaporate minus precipitate. So in Earth climate, people have a name for that quantity. It's E minus P, the evaporation minus the precipitation. So E minus P in the south, that difference in evaporation minus precipitation must equal the difference in amount of power that's available here than here. Okay? Is that clear to everybody? And so you see the seasons are asymmetric. And this is, I think, the explanation for why all the lakes are on one side of Titan rather than the other. There's more sunlight at peak available to evaporate minus precipitate the methane here than here. Now, the amazing thing to recognize is that this effect that I told you about, the alignment of the seasons with the orbit, changes with time. All the planets tug on each other gravitationally. Every time Jupiter is especially, he's the bully in this game. Every time he comes around, because Jupiter is so massive, he tugs on all the planets. And all the planets do this to each other too. And these mutual gravitational tugs that the planets apply to one another change the orbits of the planet and the spins of the planet. So all the planets dance around like this. Okay? And the Earth does too. For the same reason, Saturn's orbital parameters change. And Saturn's tilt axis, so the obliquity changes. Here's a plot of the obliquity going up and down. Here's the eccentricity of Saturn, so how elliptical the orbit is, how much closer it comes to the sun, further away. And this alignment angle between whether southern summers are close or northern summers are close. All of these things change every tens of thousands of year period. So this special arrangement that I told you about actually flips around. And this is the situation today. Southern summers are hot, northern summers are cold. 30,000 years ago, exactly the opposite was the case. So here, northern summers are hot, and southern summers are a little bit colder, a little bit less intense. So this is really quite amazing that the energy difference between north and south flips with time, with tens of thousands of year period. The reason why I say that this is amazing is because the very same thing happens on the Earth. So this is this angle that measures the alignment of the orbit. The precession index is plotted here for the Earth, the obliquity of the Earth, the tilt of the axis, the eccentricity of the Earth. All of these things vary at time. And then people realized a few decades ago that they can measure the amount of sunlight that the Earth gets at a very special spot. Somebody made this spot, and you wouldn't believe the number of papers that have been written about why the 65 north at summer solstice is the right time to measure the solar energy on the Earth. But if you measure it, you get this trace. You get these wiggles. I'm sorry it's not projecting well on this projector. Okay, so there's some special place to measure the sunlight on the Earth that gives you this, the amount of solar forcing, the amount of sunlight that the Earth gets. Okay? What people realized, and this was one of the most influential theories in climate science of the Earth, is that if you measure the amount of oxygen-18, the isotope of oxygen in the ice of the Earth, it correlates extremely well with these variations in sunlight. So what that says is the amount of sunlight that the Earth gets determines the amount of oxygen isotopes that is recorded in the ice cores in Greenland or in Antarctica. Now, this oxygen-18 is sensitive to temperature. Why would that be the case? Oxygen-18, say in water, so you have H2O, right? But the O could either have a molecular weight, an atomic weight of 16 or an atomic weight of 17 or 18. You can imagine that if it's very hot, you can't tell the difference between exactly what's the mass of the molecule. They all bounce around really, really fast when it's really, really hot. But as it gets colder, the difference between an atom that's a little bit heavier and the atom that's a little bit lighter becomes more significant, because now they're not moving so fast. So you can start telling the difference between molecules that are heavy versus molecules that are light. So this is a thermometer for the Earth. And if any of you have seen, say, Al Gore's movie, this is why people go down to Antarctica or to Greenland and extract ice cores and determine what the paleo temperatures of the Earth were, because this is how we can tell what the temperatures of the Earth were in the past, by measuring isotopes of oxygen or hydrogen. This connection between the oxygen isotope ratio in ice of the Earth and the solar insolation function led people to believe that there is a periodic forcing of the Earth that changes the Earth's climate every tens of thousands of years and leads to glacial cycles on the Earth, okay? So everything I told you about Titan is now a very hotly debated theory about climate change on the Earth. So people try to understand the best they can the extent to which Earth's climate varies periodically because of the variations in the orbit of the Earth. Remove that, and then see if there's anything left, if there are any long-term variations that maybe mankind is responsible for or other factors in nature are responsible for. But first we have to understand to what extent these orbital cycles are affecting the climate of the Earth. And the same orbital cycles are affecting the climate of Titan. So this is the extent to which sunlight in the north versus the south of Titan change with time. So this is 1 million years of time, and you see this is where we are today. This is where we were 200,000 years ago, and you see every 45,000 years or so, we have an oscillation. We have We have one period in Titan's history. And there's other periods that are relevant. Maybe the important one is every 270,000 years. I don't know. But what I do know is that there are these important periods that lead to climate oscillations in Titan. And there are similar periods to the climate oscillations on the Earth. I have a colleague here at Caltech, Tapio Schneider, who together with a student now, Sonia Graves, are simulating the effect that these climate variations are likely to have on Titan. So what you see here are the results of their simulations. This is hot off the presses. They're just about to submit this for publication now. And what's plotted in color here, this is, again, the same sort of plot I promised I'll show you more of before. This is time. This is one Saturn or Titan year, which is really 30 Earth years long. And this is latitude again. And this is the amount of methane on the surface in the north and the amount of methane in the surface in the south. So first of all, you see that the amount of methane in the south and in the north actually changed by, say, 10 or 20 meters every season in their model. So they can explain this thing that I told you about the lakes changing. But in addition, you see that all of the methane ends up in the northern hemisphere in their models. So there's a net transport of methane in their model from the south to the north because of this effect that I told you about, because of the alignment of the orbit with the seasons. Okay, so models are sort of now agreeing with this sort of theoretical prediction for why all the lakes are in the north. And I just want to highlight for you how analogous this is for the Earth. So this theory about climate change on the Earth being driven by orbital cycles is called Milankovitch, or really more appropriately should be called Croll-Milankovitch, because these two guys sort of thought about it at the same time. Croll thought about it a little bit before, and then Milankovitch actually calculated it correctly later on. And the idea is that these ice ages on the Earth, the growth and recession of glaciers that extend all the way down, in Montana you see a lot of evidence of glaciers in the past and some that still exist. This growth and recession of glaciers in the northern hemisphere and the southern hemisphere of the Earth is driven by the orbital variations of the Earth via the changes in sunlight is called the Milankovitch theory, or the Croll-Milankovitch theory. So there may be an analogous climate cycles going on Titan. So I'm nearly done, but I just want to tell you about what we can measure during the lifetime of Cassini. We obviously can't wait 30,000 years or 45,000 years for everything to reverse and see if all the lakes end up on the other side. But we can look at the seasonal cycle. So Cassini has been there for several years, and it's going to be there actually now. It's just been extended for another decade or so. Not quite. And one thing we could do is look at Titan over those timescales. So this is something that a former student here at Caltech, Emily Schaller, did. She actually looked at Titan through telescopes, and she saw that there were very large cloud outbursts that come and go. Those clouds also tell us something about the methane cycle on Titan, because after all, the methane evaporates and forms clouds before it rains down and transports to the other hemisphere. So that's one way we can probe Titan over seasonal timescales. The other is to stare at the same lake and see if it changes. And this is something else that Alex and I are doing now. So here is Ontario Lacus. I promised you that this was an important famous lake on Titan. You see actually there's very interesting things along the shoreline of Titan. There's one part of the shoreline where there's actually a channel draining down into it, and there's a feature that looks maybe like a delta, a place where sediment accumulates on the bottom of the lakes, sediment that's been delivered by the delta over here. There's mountains over here on this side of the lake, and then the interpretation that was just published by my teammate is that this is an erosional wave-cut shoreline, wave-cut beach on this side. So there's sort of familiar beach morphologies that we see on Titan, appearances of beaches that should be familiar to terrestrial geologists. The positional ones, erosional ones, and mountains, tectonic ones over here. What we can do is we can see how the lakes on Titan change. So here are two radar images taken 2 years apart of a collection of lakes in the southern hemisphere. You see that in this image, the lakes are there. You see these dark features appear inside the boundary that I showed here. The red boundaries are just the boundaries of the basins within which the lakes exist. You can ignore them. The cyan color here, interior to it, are these dark features that are filled with methane. Okay? In one image, in this image. In the other image, they're no longer there. You see, they disappeared. So Cassini came back 2 years later, and these features that were formerly filled with methane are no longer there. Something similar happened in Ontario. We looked in Ontario once using one instrument in 2005. I told you this was one of the first lakes that was discovered. It was the first lake that was discovered on Titan. And then 4 years later, we looked at the lake again. We looked at the lake again with the synthetic aperture radar instrument. So it's a little bit tricky to make the comparison between the two different instruments. They don't work exactly the same. But still, we think that we can outline the shorelines of the lakes using both instruments. And what was amazing to find out is that with one instrument over here, the lake was this big. And then when we looked at it 4 years later, the lake was only this big. Now you see the radar instrument has a much higher resolution. We could see the surface much better. So again, it's tricky to really assert this comparison. But we have multiple lines of evidence that suggest that indeed the shorelines have receded, in some cases by something like 20 kilometers from over 4 years. We can measure the slope along the shoreline. I won't tell you how. It's a little bit, or if you want, I can tell you after the talk how we measure the slope along the shoreline. It's about 1,000th. So the fact that the lake receded by 20 kilometers means that there was changes in heights of the lake on the order of several meters. Okay, so we have direct evidence from Titan, also by modeling the changes of these disappearing lakes, of about a meter per year variation in the methane height on the ground in the southern hemisphere. Remember, that agrees with the models that I showed you from Sonia and Tapio's work. So the models and the observations now agree. There should be about a meter per year variation in the methane level. This is roughly a meter per year variation in the methane level in the south. Okay? Not enough to move 200-300 meters of methane from pole to pole, but definitely enough for our spacecraft to measure. So let's see. Let's just summarize what I told you. I didn't talk very much about this, but I told you that we can measure the slopes leading into the lake, and we can make a bathymetry map. We can actually map out the topography interior to the lake and get the slopes in different parts of the lakes here. We can see from those slopes the extent to which the regression of the shoreline, the recession as a result of the constant drop in lake level, the extent to which that affects the lake depth. And the answer is we measured several lakes, and in all the cases we get something like a meter per year, plus or minus a few tens of centimeters. Okay, so several feet every year the lake level goes down. That's not enough to explain the changes in the lakes over long time scales, I think. And in the north, we so far haven't seen any changes, but we're very much looking. We're getting more and more passes in the northern hemisphere again now, and we'd like to see if the north, while the south is emptying of methane, whether the north is filling up with methane. So we're looking for that. And the amounts that we see a change by actually agree with some models. Other models actually predict different phasing to the changes. So some models predict that the lake should actually recede in the north in the summer season, and some models predict that it should recede in the winter season. Because remember, I told you what matters is not just the evaporation, but the evaporation minus precipitation. And you know that some places it actually rains more in the summer. So it's a little bit tricky to figure out whether the lake should actually grow or recede as a function of season. So these measurements that we're making at Titan allow us to figure out which way the seasons work on Titan. And then what I really find exciting is that the fact that there are many, many lakes in the north and very few lakes in the south is probably a consequence of the orbital arrangement of Titan that changes with time. So all the lakes are in the north now because southern summers are short and intense and northern summers are long and subdued, but the situation was different in the past. And it changes with tens of thousands of year period, much in the same way as Earth's climate cycles vary with tens of thousands of year periods. So I just want to leave you with this sort of animation that we made. There's a lot of stuff going on there, and I could spend an hour explaining to you what all these little methane molecules are doing. Some of them represent the seasonal exchange of methane from one pole to the other, and other ones represent the Milankovitch scale, the tens of thousands of year variations of the transport of methane from one hemisphere to the other hemisphere. And you see time is running backwards here from the present to 40,000 years ago. But I really hope that you imagine this world now as a place that, even though it has this strange chemistry and exotic thermophysical conditions, actually has all the familiar properties for both geologically, hydrologically, and from a climate science point of view the fact that it has seasons, it has climate cycles, it has lakes, it has dunes, it has all of these things that are strangely familiar to our own world. Thank you.